The last section we're doing today is section 3.8. That's the last section in chapter 3. This is on Newton's method. So this is something that people did before there was graphing calculators to find zeros of a function. They did something called Newton's method. And the way you do that is you make an initial estimate x1 that's somewhere close to what our actual zero is, and then we make some new approximation. The way we do that, that's x of n plus 1. We use our previous guess, that's x of n, and we subtract off the quotient of the function value at x of n and divide it by f prime of x of n. If it's within our desired accuracy, let's say we're trying to go to the thousandths, be within 1/1000th of the last guess, then that's our final approximation. Otherwise, we need to redo it until we get close enough. And each time we redo it, that's called an iteration. So we're going to use Newton's method. We're going to do 3 iterations of Newton's method to approximate a zero of x to the x squared minus 2 using 1 as our initial guess. So I'm going to rewrite the process down here. To find our second guess, we use our previous guess and subtract off the quotient of f of xn over f prime of xn. Now it's helpful off to the side to figure out what f prime is. F prime is 2x, and we have f, it's x squared minus 2. And the easiest way I think to do Newton's method is to make a really big table. We have an n column that's going to tell us how many guesses we've had. We're going to use xn, which is going to tell us what our previous guess was. F of xn, so this is the function value at that point. F prime of xn. Then you're going to divide those last two. And our last row is going to be the final answer, xn minus f of xn over f prime xn. So I think setting up a table like this makes it really organized and helpful to make our use Newton's method. So we're using 3 iterations. Our first guess is xn, that would be 1. So when you put that into the original function, that's 1 squared minus 2, you get negative 1. F prime of xn is 2. You divide those two, so negative 1 divided by 2 is negative 0.5. And then do xn, so 1 minus negative 0.5, and that is positive 1.5. In this case, we haven't needed to go out to several decimal places, but I think the more decimal places, the more accurate you're going to be. I always like to go to at least 4 or even 5 decimal places. For next, xn is 1.5. F of xn, so we're plugging that into the original function f, we get 0.25. F prime of 1.5 is 3. Dividing those two, we get 0.08333. That's 5 decimal places. Like I said, going to more decimal places will make this faster because you're going to get more accurate guesses every time. And then xn minus our xn over f prime xn is 1.41667. So now we move that down. That's our next guess. Plug it into our function, and we get 0.0069. 0. Put it into f prime, we get 2.8334. Put it into fxn over f prime xn, you're dividing those last two that we just got, 0.002451. You can go to as many decimal places as you want. That one I went to 6. And our final xn is 1.414216. So going to 3 iterations, one of our zeros is this answer. The actual zeros, in case you want to see how accurate this is, our actual zeros of f are plus or minus the square root of 2, which is 1.414214. So that's extremely close. Obviously, it was a pretty good method for finding zeros before we had things like graphing calculators to find them. Okay, next example. Use Newton's method to approximate the zeros. Continue the iterations until two successive approximations differ by less than 0.0001. So that's, in this case, it's not telling us how many iterations to do, it's telling us how approximate our two successive approximations have to be. So I actually am going to just graph it. I'm not going to find the zero, I'm just going to look at it and see where I think it might be. And when I did it on this case, I saw that the zero was somewhere around negative 1.2, so that's what I'm going to start with, negative 1.2. Remember that we need to find f prime, so I'm going to do that right away. That's 6x squared plus 2x minus 1. So that's what we're going to be plugging things into. It's always helpful to see that. I'm not sure how many iterations this is going to take, but I'm going to make my table. Making sure that there's plenty of space to use lots of decimal places. You do not have to do it this exact same way. I just think that this is the most efficient way to keep track of what you're doing. Okay, now we get the table set up. We make our first n. And let's just do that in case. 2, 3, 4. So our first xn, we said we're going to start at negative 1.2 just for guessing purposes. Plug that into f, we get 0.184. Put that into f prime, you get 5.24. Divide the two, you get 0.03511. And then take our initial x1 and subtract off what we got in the previous box, we get negative 1.23511. So since negative 1.2 and negative 1.23511 do not differ by less than 1/10 of a thousandth, we're going to need to do this again. So we're going to use our previous answer and redo. Put into the function, we get negative 0.00771. Put into f prime, we get 5.68276. Divide those two answers, you get negative 0.00136. And subtract, we get negative 1.23375. Those two are not less than 1/10 of a thousandth close to each other, so we do this again. Negative 1.23375. Put it into f, we get 0.00001. Put into f prime, we get 5.66533. We divide those two, we get seriously close to 0. And then you subtract, we get negative 1.23375. So these two are less than 1/10 of a thousandth close to each other. So the zero that we're going to use is negative 1.23375. Okay, so here's an example when Newton's method fails. So we need to make sure that we have a good zero, otherwise it'll be really hard to have an answer converge. You want to have to do several iterations. But here's a little note. Newton's method will fail when the derivative is 0 for any of our guesses. Whoops, not z. Fail for any xn in our sequence. Or, let's see this example here. So let's find the derivative, because we always need to use a derivative. Derivative is 1/3 x to the negative 2/3. So we're going to make our table. And xn, f of xn, f prime xn. Divide those two. and our final column. Okay, not sure how many we're going to do. I just want to illustrate something to you. So we're going to use, for our first guess, we're going to use 1/10. Let's use color 1/10. If we plug that into F, we get 0.46416. Put it into F prime, you get 1.5472. Divide those two, you get 0.3. And we subtract, you get negative 0.2. So we're going to use negative 0.2. Put it into F, we get negative 0.5848. Into F prime, you get 0.97467. Divide the two, you get negative 0.6. And you subtract, you get positive 0.4. Okay, let's do one more just to see what happens. Put 0.4 in, we get 0.73681. Into F prime, you get 0.61401. Divide the two, you get 1.2, and subtract, you get negative 0.8. So as you can see, it's almost like doubling in distance away from our original guess. We went negative 0.2, positive 0.4, negative 0.8, so it's actually never going to converge. And if you see that happen where you are bouncing around from negative to positive, but they're getting bigger, then it's not going to work in that case either. So in most cases it will work, but if you start with a terrible guess, something like this might happen. So you want to make sure you make a good first guess. Okay, that was chapter 3 and section 8 on Newton's method.